All right. Let's talk about the hackathon for a moment. So we're going to have a final pitch off by the 3 remaining teams in our hackathon. It's been kind of a long journey for these guys in hackathon terms. They've been working at this for a little bit less than 2 months, but from the time that we gave them the challenge and the time that they're here, it's been a little bit, like I said, a little bit less than 2 months. So what you're about to see is going to be pretty amazing. So come one, come all. A little bit about what we're doing, what the theme was this year. So this year we focused on Edge native AI hardware software co-design. And we worked together with ETSI. OCP worked with ETSI and LF Edge, and we got together and we said, hey, what resources do we have that we could pool together to kind of make a really compelling, hackathon contest? So what we have on the screen up there is kind of like what we're offering the hackathon, what we offered the hackathon contestants, and that was OCP. We provide a platform, a development platform, and a stack, right? So our development platform in this case was contributed by, we had 2 contributors that that gave AI boosted hardware in the cloud for these guys to use, and we gave them access to anything they wanted. LF Edge also contributed their Crano blueprints, which are very helpful. A lot of these blueprints have been certified to run on OCP's Open Edge hardware, so we're kind of familiar with them, but they're pretty powerful. Then we had ETSI, who contributed their Mobile Edge Cloud APIs and their sandbox, which allows developers to simulate mobile data in real time and using their APIs synthesize results, right, as if they were really connected to a mobile network. So together, all together, what they had was a sandbox. They had a platform. They had development resources. They had the software APIs to build just about anything they wanted in mobile. And they had a challenge. So what we're going to do today is, without getting too deep in the challenge, we're going to go right to the pitch-offs. So there are 3 teams remaining. The first team is going to come up here. They have 7 minutes to pitch, and they're going to present their solution. After they presented their solution, there's about a 3-minute period in which the judges or maybe someone from the audience can ask them some tough questions that'll help us. We'll see how that goes. But they have 3 minutes for Q&A, and then the next team's going to come up, right? So there are 3 total teams. That should take about 30 total minutes. After that, there's going to be about a 10-minute period for judges to do their thing. And once the judges have done their thing, we're going to come up here and announce the winners. So it's going to be pretty exciting. So Team 1 is what they called Project Shake Tower. Team 2.
We're about to start a hackathon at the Expo Theater. If you'd like to join us, come on over. Thank you.
Team 2 is Green Cyclops. And Team 3 is Team Palk. So we're running out of time. Let's get started. Let's find out how this turns out. So I'd like to introduce Team 1, Shake Tower, to come up here and present their results, their solution. Thank you.
Thank you. My name is Chi Tang, and this is Yi Han and Sharu. We are Shika folks. So, yeah, let's get started. So, the problem we are trying to solve is to really reduce the communication barriers for people in the daily life. For example, let's say if you're traveling into a foreign country, you don't speak the same language, that will be a big challenge. Or even though sometimes you go to a place that you really need that kind of local information that you don't have. For example, you're here in the San Jose Convention Center attending the Open OCP Summit. and you want to know who is coming, who is doing the talk, and everything. It's a little bit, work to do a Google search research, but instead we are developing a easy, simple user interface, which is like a chat message box, and then that's what we do. And language, I would say, like in general, like language itself is geographically distributed. Like every different place has a different, accents and dialects. That's what we are trying to do. Also, is like really has the local people using the local information and serving for providing the service. So in contrast to, let's say, you're using a ChatGPT, that you or like some other like cloud-based service, we focus on the in-person and on-site user experience, so you don't have to be distracted by the online stuff. The idea behind that is simple, straightforward. That the language, it has a positive correlation with the location and time. Like I said, like here today, I'm pitching off the open API AI related applications. The likelihood that the language I'm using increases by giving a little bit more context, like I'm here and right now. So that improves the usefulness, accuracy, and relevance of the chat. About Shaker Tower, we are inspired by a Nintendo game. Like the name is Zelda, and inside the game, the hero Link using kind of like a iPad, we call like Shaker Slate, connecting to a tower that is nearby. The tower is not like serving like just like cellular tower to the internet access, but also has an edge server, like things like you can store or cache some local database, and had some sort of a little bit of computation resource that we can leverage for. We are building the Shaker Tower, which is essentially the local AI virtual assistant applications. The data is provided by the local service providers. Like today is like event hosts that can provide the schedules of events uploaded to this platform. So the people nearby or people attending to this event can easily access to. How do we scale is like we are hoping for collaborate with the mobile network operators. They are like the operators like you like buy the 5G service or 6G service later on in the future. Like you want to buy an AI service, like you want to have a local service that is really relevant and useful for you. So the implementation of this, we have basically 3 parts. The app side, we developed the user interface app that is the chat box that user type in the text and image or audio files uploaded to the MEC server that is hosted on the Edge server that is having the vector database. The useful information, and then the data is transmitting. We do the layer of wrapping that we query the customer database and add it to the user input, connect them together, and then send into the cloud side, which is the large language model, and giving a response. I think I will hand over to Yi for more information.
Yeah, so what it actually looks like in our UI. We are right now at San Jose downtown. So in this area, under the same zone ID and cell ID, all the available service provider will pop up. So for example, this Egyptian Museum and the current OCP Summit. And with each service provider, we have the database. So those 2 pictures are examples of when we're actually chatting with our assistant, what they will give us. In the first one, please ignore the found database. That's just for demo purposes. After I say hi, they actually find out, oh, now it's morning, now we're at the OCP, so maybe it's time for breakfast and registration, right? And another example is when I look for someone, I found so many great developer, but I forgot his family name. And this can easily help us identify who was the person I talked to and where and when to find this Andy. Another example is you can do really good context-aware search within incomplete input. For example, Sonic. When I look it up in search engine and other large language model, it told me it's a hedgehog from a video game, which is very famous, very cute. But under this context, you actually find the right concept for Sonic. Again, tell me where I can attend more Sonic workshop in the future. We can also take a multiple format, like image, and this is another demo for Egyptian Museum 1. Given the time limit, I'll hand over to Sharu.
Okay, thanks, E. Let me summarize the benefit and beneficial of our solution. 3 takeaways. First is the super user experience. As we can see, since we have a localized database provided by service provider like the museum event host, we can gain a lot of local context. Okay, I'll be really quick. And then the second benefit is that the secure and the privacy, the private data like photo and some user profile, they live in the Edge server. They won't be sent to cloud. And the last, we optimized using the Edge server because it's local. So the server is very close to our users, so we can really make a very low latency search queries. That would be the 3 main takeaway, main benefit of our solutions. Thank you. Any questions?
Anyone ask them?
Already asked all of my questions.
Very impressive. So is it the main idea, the local ChatGPT?
Yes, the main benefit is the service provider, like the event host, the OCP Summit event host. You can upload your own local database. It's a federated database. And we are a platform to host that local knowledge. So compared to the bare-bone ChatGPT, we will provide actual information, give the agent some local context, so they will provide a superior user experience.
Yes.
Yeah.
So you mentioned about the family name for the person I met and I forgot their name. So that is image recognition, right? And that is built in?
I can take it. So it's like, say, I only remember the first name of a speaker like David, but I think he's working on, say, in Meta, and I cannot remember the exact name. So I can ask the AI agent, who is this speaker? And the AI agent will find all the information and the event that the speaker will give.
So it's context plus
Yes.
half information, not like image recognition. Okay, thank you.
We put this database last night, so it's very easy to implement. But the family name you mentioned is actually public information. It's just a quick demonstration how we can leverage those databases for the future. Like, for example, if we work with a museum, we will work with them to build their database. They own the data, we don't own the data. We just provide the solution.
Okay. Thank you, guys. Team 1, thank you. Big applause. Great job. Now we have Team 2.
Hi everyone, I'm Santiago Rodriguez and this is Fernando Lamela, and we will introduce you our solution, Green Cyclops. Okay, Green Cyclops is a computer vision platform that Green Cyclops is a computer vision platform that with the support of 5G, edge computing, and artificial intelligence, can retrieve information for the surrounding environment, analyze it, and take decisions and perform some actions related with the natural environment surveillance and smart agriculture management. The information sources can be fixed cameras, drone cameras, or even IoT devices. We have two parts. The edge part, where the application okay, where sorry. Okay, we run the inference at the edge. We have one instance application that can run several pipelines running different models from different video streams. We have two, a cloud management, and we can see all different models of our solution. We have the make services used for retrieve information about the location, the power and quality of the signal, and so on. We have the AI and IoT instances that process information from the cameras and the IoT devices, and with the inference produce some events and alarms that are sent to the cloud. At the cloud, we have a model repository with pre-trained models that can be used by the instance at the edge. So when a new information source appears, it sends a message to the instance at the edge notifying the location of the video stream and the object to be detected. The edge retrieves the model to be used, generates the pipeline in real time, and produces the results that are sent to the Green Cyclops management at the cloud.
Okay. As the detections are made by the inference models that we deploy in the application instance at the edge, events are generated. These events, as well as events from the IoT hubs, where we retrieve information, pass a correlation process to raise an alarm. With this alarm, at the same time, we can raise different actions in real time, like, for example, request to a drone to move the gimbal or to approach, to go closer to the location where the alarm is being produced. And at the same time, this alarm is sent to the management side that we have deployed in the cloud. In this management side, we can raise and group these alarms into issues, and we can have all the information about all the scenarios we support in the Green Cyclops solution. That can be, for example, fire prevention, deforestation, information, or different use cases related with smart agriculture, like the detection of wildlife intrusion into production land. We have in this management side all the information retrieved from the alarms with the snapshots, the relevant snapshots from the detections of the different inference models we are running on the edge side, and we have all the traces of the applications we have running at the edge. These traces and the monitoring of this application allow us to maintain the SLA of these applications running at the edge, having the capability to move this application between the different kind of edge. We can configure different kind of resources, different kind of paths. We can, with this path, we can have actions to request more flights as a real-time action to retrieve more information from a location with a specific path. We can set new devices, UAVs or fixed cameras or another kind of IoT hubs that can be configured in the solution. And we have information from the radio retrieved from the APIs. We are because we have integration with the APIs from the ETSI part. We are using or reusing all the work from the Akraino project in three kind of themes: the AI Edge, the 5G MEC system, and the smart cities. From one of them, we retrieve or we are reusing information or taking information related with the use of Edge for surveillance and security scenarios. In another one, we are using, for example, we are taking how to process or use the 5G connectivity to process video streams. And in another one, the inclusion of different kind of sensors or IoT hubs for smart agriculture. We are using different APIs from the ETSI, like location information or radio network information, or the APIs for registering the applications we deploy at the edge. And we have, as I say, a backend where we can manage all the SLAs related with applications we have in the different sites of the solution. And that's all.
All right, you guys have any questions?
Hi, thank you.
Hi.
Thank you for the introduction. So I have a question. You mentioned that you're using the GSMA SBI. I think we talked a little bit yesterday, the east-west bound APIs. Can you describe a little bit more?
Yeah, we are using the SBI. Excuse me. We are using we have integration with the ETSI APIs. We are using the SBI's definition from the GSMA, for example, to retrieve analytical information for the NWDAF. And we are using for federation. In the demo, we don't have a federated scenario regarding the edge. We can define in the sandbox in order to extend the demo. But we have integration with the east-west bound interface definition of the GSMA that are defined in the OPG and in the OPAC to be capable to put this solution in a scenario where we can use another edge nodes from another providers or another operators we can work with.
Okay, so potentially you can support multiple operators network.
Yeah,
okay.
We try to.
Thank you.
I think this is very scalable. And when you do the Alpha Edge, AI Edge Blueprint family, did you change any code or you just download and use as it is?
We are, for example, when we change the application between edge nodes, we are monitoring two kind of events. One events that are from the retrieved from the application, like the evolution and the uses of the resources in the edge of the application, and the network events, what we can retrieve from the APIs, for example, in this case from the ETSI. We can have in one case to request to the same node for more resources. If no more resources are available at this node, we can move or make available the application in another node. There are another use case that is UAVs that are moving, and we detect, for example, that the latency are not the desired latency we request in the SLA when we try to deploy the application. And in this case, we deploy the application to be used for this drone in another node. We have tests to move not only the application and to move the context of the user, but in this demo we don't have this use case deployed. This is only a use case that we have in the lab, and we need to work more on that.
One more.
Hi, thanks for the presentation. So, yeah, it looks like you are federating a lot of different kind of devices in your solution. So, just wonder, like, do you have a plan to productionize it after the hackathon? And what are the major challenges you would think of if you want to make it at a large scale?
Yeah, our intention is to move this proof of concept to a solution that we can deploy in an environment. In fact, we are talking with an operator in our region and some customers that can be interested, like governments, for example, with the scenario of fire department, or fire detection, or fire prevention. Yeah. And our plan is to go to continue with the roadmap of the development of the solution. In fact, we have a split in the development of the solution. We have, from one hand, the Green Cyclops solution that is composed by a set of devices and principally software and applications. The applications that we deploy at the edge and the application that we deploy at the cloud for the solution, the whole solution, end-to-end solution. And we have another development that is in charge of all the, in brackets, magic of the maintenance of the SLA of the application in the edge nodes. One of them, the last of them, is cross. We can be used by Green Cyclops or another solution we have, or another partner can have. And Green Cyclops we have the orientation to be used to protect the environment, or to be used to digitalize agriculture or smart or first-class industry. Like this.
On the first slide, just
thank you.
I'll see intro.
All right, thank you, Team 2. Appreciate it. Great job. Great job. All right, here we go. Team 3, let's go. You can.
Hear me, right?
Yes.
Yeah, okay. So I'm Vignesh. This is Vijay. We represent Palsy Networks. So in Palsy Networks, we are part of the open disaggregation. We build softwares in the open disaggregation network. So what we do is we build software and we work with hardware vendors and sell it as a bundled solution. One of the typical problem that we see is whenever there is a problem on the hardware, the only solution or only option that we have is just to send it back to the manufacturer so that they can do an RMA. And so this is a problem that takes more time, and we are not even identifying what is the actual problem. So what we thought is we can come up with a platform which can identify or predict even before the problem has happened. If we can predict the problem and provide a solution, it will be useful both for the manufacturers and also for the user to mitigate from the problem. So what we have built is a prototype, a platform which will monitor different types of hardware components. At least in this demo, we are concentrating more on the hard disk part. But this is a platform that we wanted to build for all the hardware components. And the other objective also what we had is to have a lightweight model so to infer the results. Yeah. So this is the idea what we have, and probably I'll hand it over to Vijay to give more info on the product. Yeah.
Yeah. Good evening, everyone. So take an example. Today's everything is working here, and some of the devices stops working immediately. What is the option we have? We don't have the options. In the software, you have the options. You can reboot the device. But if hardware fails, you don't have the option. You need to replace the hardwares. But if we have something which can tell in advance that, okay, this hardware may fail, so you have the options to carry additional redundant hardwares, or at least plan in another way. So take an example of the data centers. The hard disks are the heart of the data centers. If hard disk fails, data losses happens. There are lots of financial losses, as well as organizational reputations goes down. So what we have developed here is basically a predictive maintenance solutions, where we have monitored around 1 million hard disk data sets. And we have trained our AI model so that it can predict the failures in advance. So in our solutions, there are two major things, basically. One is the data sets which we collect from different multiple vendors, then we train, and then the platforms where our AI model can learn. So we, thanks to the OCP Foundations, who has provided us the platform where we have run our CI pipelines, where our model has been trained up. And once our model trained, then we deployed into certain our labs. Even we have a live demo here on our booth. There you can visit and you can see that, okay, it's really working. You can bring any hard disk and it can predict its states, basically. So how it works is basically like we have multiple data sources, and then we do the data ingestions and then pre-processing of the data, and then we train our model. The best part of our model is like it's very lightweight. Even we can predict the failures on the edge device itself if it has enough processing powers. Take an example of the 5G radios. And there are multiple hopes around those 5G radios. If 5G radio itself fails, what we can do? We lose the connectivity. Now, if your model is optimally enough, it can predict there itself the failures, and it can just pass on the information to the admin. Okay, there is a problem going to happen, so please plan to rectify that situation. So for the hard disk failure predictions, we have used smart attributes. There are like around 256 attributes which are already available from various vendors. Some of them is like relocated sector counts, reported uncorrectable errors, current pending sector counts, uncorrectable sector counts. These are some of the examples of the attributes which we have considered to predict these hard disk failures. So we have built a very basic user interface right now because of the time crunch. And in this interface, like we can extend it to like any hardware. Right now, our current POC is for the hard disks, but like we can extend it to a Wi-Fi module or a power systems, or maybe a CPU, or maybe another, I would say, a robot, any hardware device, or maybe any hardware component in assembly line. So if, as long as we have the data sets to train our models, we can do. So for that, even we would like to invite the communities to come up with an standard APIs for the hardware stats, basically. If every vendor opens up, now is the era of the white box hardwares. Everyone is coming up with the open heart. You take my data, help us to identify that what problems can occur in my hardwares. Take an example of the electric vehicles. So now, like in next decades, the diesel vehicles will move away and only electric vehicles comes, the smart vehicles comes. If we have the data, we can predict in advance that, okay, your car may have some issues, so take care of like repairing it. Now, even the user will get the information which component will fail. We analyze the data and give the information in advance to the users. It helps our life making better and better. So we have scope to expand to like, it's like C. So we have started with an idea, and we would like to extend it to all aspects of the hardware failure predictions. Yeah, thank you.
You guys have any questions?
Thank you. Very good presentation. You mentioned about EV. So you just consider the whole EV as one piece of hardware, or you just look into the resources within EV and remote manage it?
Exactly. So there are two aspects, like because EV is a very big system itself.
Mm-hmm.
So we are specific to the each components, basically within the EVs, which component may fail. So we give like take an example in one of the slides, hard disk is one of the component, but in the system there are hard disks, there are network line cards, there are Wi-Fi modules, there are other sub-assemblies. So we consider like an entity which can gives us the information regarding its lifespan, regarding its decaying over the period of the times.
Yeah, thank you very much.
Thank you.
So if you wanted to scale this, right, and you had like 10 trillion devices, how would you scale it?
Yes, that is a challenge. However, like we right now, like we have used the MongoDBs basically to store and process more and more data, but we definitely need the GPU powers only for the training part. Once our model is trained, then we utilize very minimal powers. Only thing is how we make sure that okay, the communication channels keeps running for all those million devices. So we periodically update those trained models on those devices. So we do not hog the CPUs that okay, every milliseconds you pull the data. No, our model is trained and it put into that particular nearby edge. So that can take care of the prediction of failure of those devices. That's how we can scale.
So you have a cloud for your training your models in the cloud, right?
Yeah.
How often do you train the models and push them down to the edge?
Yes. So right now, like we have trained like okay every 24 hours, but that frequency can increase or can decrease depending upon like the new hardwares. So right now, like we trained our model on like last 6 years hard drives datas. That was huge data. Now we start with the new hardware. Then like okay, initially learning period is more. Then later on, like the training of the model may not be like that frequent, as long as you are not getting some different data sets.
Thank you.
Thank you. Thank you very much.
All right, Team 3, thank you very much.
Thank you.
All right, as judges, we're gonna like huddle for a little bit and give us a few minutes, and then we're gonna see who the winners are.